Hey everybody, and welcome to our 11th video lecture. Today we're going to be talking about parametric surfaces and how to calculate their areas. Now you've already seen some calculations of surface areas back in your previous calculus classes, especially when the surface was the plot of a single function. But just like parametric curves can be much more complicated than graphs of functions, parametric surfaces can be a lot more complicated than their counterparts, and we can still come up with ways to calculate their surface areas and to think about them, and also just to graph them. Let's start by thinking about parametric curves. So to describe some sort of curve in R3, I give you a function r of a single variable t, which has an x-coordinate, x of t, a y-coordinate, y of t, and a z-coordinate, z of t. And if I'm thinking about t as the time, then as t changes, I go from my starting point, and I could spiral around and do all sorts of fun and crazy things over three-dimensional space, depending on what the values of x and t and y and t and z of t are, and end up somewhere at my ending time. Now, a curve is a one-dimensional thing, and this is indicated in a lot of ways, one of which is the fact that it just involves a single variable, or a single parameter, t. For a parametric surface, the big difference here is that we're going to have two different parameters. So for a parametric surface, I'm looking at a function r, which is not a function of t, but rather a function of two variables, u and v. And it has values, which are x of u and v, y of uv, and z of uv. So for one example, I can think about the parametric surface described by r of uv equal sine of u cosine v, sine of u sine v, cosine u. And I'm kind of wondering here what kind of surface this draws out as I let my parameters range. Let's say u ranges between 0 and pi, and I'm going to let v range between 0 and 2 pi. So what kind of surface does this draw? Well, if I think here, this first coordinate is my x value. The second coordinate is my y value, and the third is my z. And if I calculate x squared plus y squared, this is going to be equal to sine squared u cosine squared v plus sine squared u sine squared v. I can simplify that as sine squared u times the quantity cosine squared v plus sine squared v. And of course that's the same thing as just sine squared u, which if I look at what z is the same thing as 1 minus z squared. So every point on this surface is going to satisfy the equation x squared plus y squared plus z squared equals 1. So I'm looking at a surface which satisfies this equation x squared plus y squared plus z squared equals 1, and that immediately should make us think about the sphere. And specifically the sphere of radius 1. And what this says then is that the surface that I'm drawing is going to have to be at least it's going to have to lie on the surface of the sphere. It doesn't necessarily have to be the whole sphere. We don't know that yet. But if I also think now about spherical coordinates, in the spherical coordinate system, to write down a particular point on the sphere of radius 1, I'm just going to take rho to be 1, and I'm going to let phi and theta be whatever they want to be. So the corresponding points on the sphere are all of the form sine phi cosine theta, sine phi sine theta, cosine phi, as in the spherical coordinates phi ranges between 0 and pi, and theta ranges between 0 and 2 pi. So this is exactly giving me the whole sphere because it's exactly how we describe the sphere in spherical coordinates. Let's look at another example. In this example, I'm going to let my parametric equation be 2 cosine u v and 2 sine of u. In this case, I can check that my x value and my y value here will be related. And specifically, I can see right away that x squared plus y squared is always going to be equal to 4. So this is going to be a surface which lies on the cylinder in three-dimensional space, described by x squared plus y squared is equal to 4. Oh, and I'm being silly, aren't I? This is not y, this is z, isn't it? So it's x squared plus z squared equals 4. So this is a cylinder which is going to be centered around the y-axis. Like so. And the radius of the cylinder from the y-axis, the radius across is going to be 2. And since there's no restriction here in the value of v, I'm not demanding that the range of v be between any two values, the cylinder goes on indefinitely in both the negative y and y direction. And I also haven't restricted u, so I go around completely full circle, and I get the entire cylinder here described by the surface. As a third example, let's think about the parametric equation describing a surface given by cosine u plus cosine v, sine u plus sine v, and v. Let's try to plot this. This time it's harder to get an equation that describes a relationship between x, y, and z in a shape that we're familiar with. In fact, this is because the shape that we're going to make is not one of the shapes that we are familiar with. But what I can do here is I can choose, maybe a specific value of v, such as v equals 0, and see what u does when for that fixed value of z. So when v is equal to 0, I get this equation of a certain curve on my surface. This curve is given by r of u0 equals cosine u plus 1, sine u, and 0. And this is actually a parametric equation describing a circle in the xy plane. It's not a circle centered at the origin, but it's a circle centered at the point 1, 0 of radius 1. So let me draw that circle in here like this. And I can do that similar sort of procedure. I can also see what happens when v is equal to another number, say pi over 4. And this is going to describe another curve on my surface. And it's given by cosine of u plus the square root of 2 over 2, sine u plus the square root of 2 over 2, and pi over 4. So this is going to be a circle in the plane z equals pi over 4, which is again a circle of radius 1, but it's centered at the point root 2 over 2, root 2 over 2. So it looks something like this. And then similarly, I can do when v is equal to pi over 2. And in this case, I get r of u pi over 2 equal to cosine u sine u plus 1 pi over 2, which is going to be a circle which is centered at the point 0, 1 pi over 2 in the flat plane z equals pi over 2. So it's a circle up here. And continuing on this way, we end up with a lot more circles, which are following a pattern of rotating around the z-axis. So what the actual surface is doing is it's forming a tube which encapsulates all these different circles, but rotates around the x-axis, kind of like one of those fun slides you see at the playground that corkscrews around a little bit, like this picture I've included right here, where it's spiraling around some axis, like a z-axis, which is in the center of it here. And that's what our plots were showing us. So yeah, that's definitely not a surface that we are familiar with an algebraic equation for, but it's one that we can plot using parametric equations for surfaces. So this is like a pretty cool tool that we have. One of the things that we'd also like to be able to do is to go the other direction, and that is, given a surface, I would like to be able to find a parametric equation which describes that surface. And one of the interesting things, of course, about parametric equations is that there are lots of different parametric equations which describe the same object. This was definitely true for curves. When I was thinking about parameterizing a circle, there were a lot of different ways I could do that, or a line, or anything like this. And surfaces are more complicated than curves, so they have that many more different parameterizations. For example here, I can think about the cone described by z equals the square root of x squared plus y squared. Graphically, this is just this upper part of a cone, so it's not the lower half at all, because I've already taken the square root and taken the plus part. But this is the surface that I'm describing. And there are a couple different ways to parameterize this. One feasible parameterization is just to take r of u and v, and I'm just going to let x be u and y be v. So it's the most obvious parameterization in the world, and then in order to get my surface, I'm going to have to let z be the square root of u squared plus v squared. And this is a very nice, easy way to parameterize this thing. But it might not be optimal in the sense that sometimes we might have to use our parameterization to do integrals or something like that. And then in that particular case, I might end up having to integrate square roots here, which is not a pleasant experience. So we might want to find a different sort of parameterization, maybe one that involves trigonometric functions, because sometimes that might make problems that we have to deal with easier. And I notice here that there's some symmetry in the sense that at any particular z value, I've got a circle of a certain radius. At that particular z value, I'm actually getting a circle of radius z. So this gives me the idea for the parameterization, r of u v, where I'm going to let my v value be z. So z is just going to be v. And then at that particular point, I need to describe a circle centered at the origin of radius v. So I can do that with v cosine u, v sine u. Now, on this particular parameterization, I need to be careful because I don't want to allow negative values of z because I'm only doing the upper half of the cone there. So I'm going to also specify v is greater than or equal to 0, and that makes sure that my z value there, that third component, will always be positive. And I can limit my u values to go between 0 and 2 pi, because if I do any more than that, I'm going to loop back around again and again and again, and I'll sort of like over-parameterize my surface. So this latter parameterization can definitely be very useful in comparison to the previous one, just because there aren't any square roots anymore. The previous example was a special instance of something we're very familiar with, called a surface of revolution. Now, I'm not talking about revolution in the sense that we're going to go grab our muskets. I'm talking about taking a curve, say some sort of curve in the xy plane, and I'm going to spin it around either the y-axis or the x-axis. And I could also spin it around the z-axis if I'm thinking about some curve in the xz plane or the yz plane. Let's just think about here spinning this around the x-axis. And when I do that, I generate a surface. And we've been talking about, even back in Calc 1, we talked about how to calculate the, say for example, the surface area of objects like this, and that sort of thing. But we can come up as well with parameterizations of these sort of objects. And the basic idea here is if this curve is given by y equals f of x, then at any particular x value, I need to be able to produce on the surface here a circle which has radius given by f of x. So a natural parameterization for a surface of revolution like this is r of uv is equal to, well here I'm going to let x just be v, and then in the yz plane, in this particular case by the way, the z-axis will be coming out this direction, so it's a little bit different than what we usually do when we're drawing these things. But in the yz plane, I'm going to be generating a circle of radius f of x. And to do that, of course, I can use sines and cosines. So I can just do x, which is v, so it's going to be f of v cosine of u, and f of v sine of u. And I can even limit my u values then to go between 0 and 2 pi, because that'll pick up the full circle there. And that way at any particular v value in the yz plane, I'm generating a circle of radius f of v, so this will parameterize my surface of revolution. And if I just want to go and do a finite surface which starts at a particular x value and stops at a particular x value, I can also bound v. And, of course, I could rotate around the y-axis instead, or I could rotate around the z-axis, and the parameterization is going to be a little bit different, but very, very similar. For example, the previous surface was a surface caused by rotating this line here, this straight line which forms the edge in the yz plane, just rotating that around the z-axis. So at any particular z value, so v I'm fixing to be v, I'm picking up some sort of circle of radius f of x, and f of x here was just y, or z, which was v, and it wasn't f of x, it was f of y. But yeah, so I was just rotating that curve z equals y around the z-axis. Now, one of the wonderful things that having a parameterization of a surface does is it helps us to calculate the tangent plane of a surface. We were talking about tangent planes of the surfaces much earlier in this class when we were thinking about gradients and things like this, but there are surfaces we're given by we're given by just algebraic equations like x squared plus y squared plus z squared equals 1. Here I want to think about tangent planes of surfaces which are described by parametric equations. For example, r of uv equals 2 plus cosine v times cosine u, 2 plus cosine v times sine of u, and sine of v. And I could notice that if I plug in u equals pi over 4 and v equals pi over 4, I end up with the point the square root of 2 plus 1 half, the square root of 2 plus 1 half, the square root of 2 over 2. So this is some point on whatever surface this parametric equation is describing. And I can ask, okay, what's the local tangent plane at that surface? And it's actually really very easy to do. I can even draw a nice little graph of this particular surface, which has a very familiar shape. It looks a little bit like this. In particular, it's a donut shape. Or mathematically, we like to call that a torus, just so that we don't get hungry. And the point that I'm looking at is where x and y are the same, and z is root 2 over 2. So it's some sort of point like over here-ish on that surface. And I can think about the tangent plane, which is this guy coming right here, And I'm trying to find an equation for that tangent plane. Trying to figure that out. Now, the nice thing that I can do about this is I could think about making a couple different curves on my surface which pass through this particular point. And the first curve I want to make by fixing my value of u and letting v vary. So I'm going to let u be fixed at pi over 4 and just let v change as we move around. And that's going to move, in this particular case, in a curve that goes around like this. That's the curve that's parametrized by r of pi over 4 v. So I only have one free parameter there, so it's not drawing a surface that time. The light blue is drawing a curve, just one-dimensional thing. Alternatively, what I could do is I could let u vary and keep v fixed at the value that I'm interested in, and make a curve r of u pi over 4. And in that case, if I plug that into my parametric equation up here, v is stuck at pi over 4, so in particular, the z value is fixed at root 2 over 2, but the u and the v values are changing. So in that case, what I'm ending up doing is I'm following my surface, passing through this point, and going around in a fun little circle like this. So these generate two different paths. And what I can do is if I take the derivative of either one of these parametric equations for those curves, that'll give me a vector in the direction of the tangent line to the curve. So in particular, if I take the derivative at this particular point where they intersect, I'm going to have a little tangent line, one in this direction, which will be a vector in my plane. And if I do the same thing for the light blue one, I'll have a vector in this direction, which will be in my plane too. So this is a really nice way to get two different vectors in my plane. Specifically, two vectors in my plane are just taking the derivative of the light blue curve, so that's ddv. It's a function of a single variable, so I can do regular derivatives, not partials, of r pi over 4 v at v equals pi over 4. And I can also do ddu of r of u pi over 4 at u equals pi over 4. Now, one thing that we might notice, of course, is that these are just the u and v derivatives, the u and v partial derivatives of the r vector. These are just, I'll call it r sub u at the value pi over 4, and r sub v at pi over 4. So I've got two different vectors that are in my plane. If I've got two vectors in my plane, I know a good way to get the normal vector of the plane. What can I do? I feel like this is on Blue's Clues. What should I do? I should take the cross product, right? So let's take the cross product of those two and get a normal vector. And that'll just be RU cross of RV. And I'm just going to evaluate that at the point pi over 4. And that'll give me a normal vector to the plane at the particular point. So once I have a normal vector, plus I have a point on the plane, which of course is the point that I started out with, I can easily write down the plane equation. That's something that we've done many times. But let's go ahead and give it a shot here. So what is r sub u? R sub u. So r up here was this equation again. Let me copy that. So r was equal to 2 plus cosine v times cosine u, 2 plus cosine v times sine of u and sine of v. So r sub u is going to be minus 2 plus cosine v times sine of u, 2 plus cosine v times cosine of u, and 0. And of course we can evaluate this at the particular point. At that point, pi over 4, pi over 4. And I'm getting r of u there equal to minus the quantity root 2 plus 1/2, root 2 plus 1/2, and 0. Similarly, we can get r sub v, and I can plug that in at pi over 4, pi over 4. And there I get r sub v is equal to the vector negative 1/2, negative 1/2, root 2 over 2. So my normal vector is just going to be given by taking the cross product of these two, which is going to be given by minus 1 plus root 2 over 4, 1 plus root 2 over 4 is 0. But I realize here that I made a sign error because the middle term was positive. So that should be positive there, and the normal vector should be 1 plus root 2 over 4, 1 plus root 2 over 4, root 2 plus 1/2. And this just sticks out orthogonally from this tangent plane as a normal vector to the plane, with this green vector here. So the equation of the plane is just coming from the usual point-slope formula, but in 3 dimensions. So I'm going to take the dot product of the normal vector with x minus x naught, y minus y naught, z minus z naught, and I'm going to set that equal to 0. Now, the point that I have on the plane, x naught, y naught, z naught, is given by root 2, 1 plus 1/2, root 2 plus 1/2, root 2 over 2. So taking this dot product, I get the equation of the plane to be 1 plus root 2 over 4 times x minus root 2 plus 1/2 plus root 2 plus 1/2, 1 plus root 2 over 4 times y minus root 2 plus 1/2 plus root 2 plus 1/2 times z minus root 2 over 2. And I forgot to parentheses there. There we go. I just set it equal to 0, and there's the equation of my plane. So the big takeaway here is that if r of v parameterizes a surface, then r sub u of uv, the partial derivative with respect to u, crossed with r sub v of uv, the partial derivative with respect to v, will be a normal vector to the surface at the point r of uv. So it'll be a normal vector of the tangent plane at that particular point. So if I draw a random surface there with some light shining off of it, and I think about a particular point there, r of uv, just by sticking in those parameters u and v, it's going to be some point on my surface. And I think about that tangent plane, well, then to get a normal vector there, I'm just going to take the cross product of r sub u of uv and r sub v of uv. The next thing I want to talk about is surface area for parametric surfaces. To start out, I want to remember that if I have two vectors in three-dimensional space, let's call those vectors u and v, I can form a parallelogram by completing these by adding another vector opposite of v over by u and opposite of u over by the tip of v. And I get a nice parallelogram here, and the area of this parallelogram is given by the magnitude of the cross product. This is the main tool that I want to use when I develop my equation for the surface area of a parametric surface. To start out, I just want to consider a random parametric surface, which I've drawn in blue, and is parametrized by r of uv. I can think about that parametric equation as being a function which takes points from the UV plane into points in three-dimensional space. So in particular, let's imagine that it takes some sort of rectangle in the UV plane and it maps it to my parametric surface over there. That means every particular point in that rectangle in the UV plane is going to be mapped to some point on that surface via this map, r of uv. And if I take a whole grid of points, it'll be mapped to a whole grid of points on my surface as well. And now I'm going to make an approximation of my surface just by playing connect the dots. And I'm going to connect every adjacent grid point to the next adjacent grid point, creating something like a quilt of tiles, where each tile is a nice parallelogram. And if I put those all together, I get a purple surface. And the purple surface is a little bit different from my blue surface, but it's pretty close to it. And in fact, if I make my grid much finer, make it a very fine grid, then the approximation I get, the quilt that I get via the purple, will be very, 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 very close to the blue quilt, or the actual blue surface. And that means that the surface area of that purple quilt will be very close to the actual surface area of my blue surface. And the nice thing about the purple is I know how to calculate that surface area. I can calculate individually the surface area of each of those patches of my quilt, and if I just sum them all together, I get the surface area of the whole thing. And we can parameterize that. If I let A be a point and B be the point of the first point in the grid in the UV plane, and I let delta U be my step going from my first point to my second point in U, and delta V be the same step in V, then I can figure out exactly what these points are in XYZ space just by plugging in the associated values. And in particular, I know how to get that area of that parallelogram there. I'm just going to take the magnitude of a cross product. So I just want to figure out that vector, which is representing that left side, and it's going to be the difference between r of a b plus delta v and r of a b, because those are the associated points. So I'm just doing r of a b plus delta v and minus r of a b, and that'll be that left vector. Similarly, the right vector is given by the difference of points, where I'm just going to plug in r of a b plus delta v, or sorry, a plus delta u b, and just take the difference there. So that vector on the bottom there is given by r of a plus delta u b minus r of a b. And if I take the cross product of these two things and take the magnitude, that'll be the area of that first patch of the quilt. If I call that patch R1, that'll be the area of R1. So area of R1 is equal to the magnitude of r of a b plus delta v, or a plus delta ub minus r of a b crossed r of a b plus delta v minus r of a b. So to get the, let me adjust that there. Now to get the whole area of the purple part, that purple surface, I'm just going to sum over all those different rectangles. So the surface area is of the blue is going to be approximately, and since it's approximate, we use squiggly equals. It's going to be approximately the sum over I and sum over j, because I need to sum over all the different rectangles in U and V. And these are indexed by I and j. So in fact, if I just let R1 be really R11, the next one be R21, and R31, and then going up R12, and then R22, and so on. then this is going to be the sum over I and sum over j of the area of Rij, but the area of Rij is going to be given by the magnitude of the cross product of the associated vectors. And if I'm using what those corresponding points are, this will go a sum from I equals 1 to 3, but in general, if I use a finer grid, I can have more than 3. I can have m, and j equals 1 to 3 as well in this picture, but I can again go to n, and this just be the sum over I and j. And let me just index those particular points in the UV plane. So I want to generalize this equation, which says that the first point is a plus delta ub, and the second point is ab, and in general it's going to be a plus I delta ub minus a of I plus delta u minus 1b, and that's so on and so forth. Or just in terms of a notation, ui and vj, I can write this as the sum over I and sum over j of r of ui vj minus 1 minus r of ui minus 1 vj minus 1, cross with r of ui minus 1 vj minus r of ui minus 1 vj minus 1, where I'm defining my ui's and vj's based on the grid in the UV plane. So A is u0, u1 is the next point if I move over in the u line, and v0 is my b, v1 is b plus delta v, v2 is b plus 2 delta v, and so on and so forth. So ui is going to be a plus I times delta u, and vj is going to be b plus j times delta v. And this should feel really, really familiar from when we did these double Riemann sums for integration in 2 dimensions. So this is our equation here. And this gives me a good approximation for the actual surface area of the surface, as long as I assume, it gives me a good approximation for the surface area, which gets better and better as I let the grid become finer and finer, so I use more and more quilt patches. And if delta u is very small, so I've used just a ton of quilt patches, then I can approximate r of ui vj minus 1 minus r of ui minus 1 vj minus 1. I can approximate this using the partial derivative with respect to u. This will be approximately the same thing as r sub u of ui minus 1 vj minus 1 times delta u. That's just linear approximation. And very similarly, I can get an approximation for r of ui minus 1 vj minus r of ui minus 1 vj minus 1. And if I do that, I can come up with a really nice new approximation for the surface area. So let's do the approximation for the second difference in red. And that says that for delta v very small, r of ui minus 1 vj minus r of ui minus 1 vj minus 1 is equal to r sub v, so this is the partial derivative with respect to v now, of ui minus 1 vj minus 1 times delta v. And then I can write down my surface area approximation. I'm just plugging in those approximations that I had before. Now is the sum over I and the sum over j of r sub u of ui minus 1 vj minus 1 times delta u crossed with r sub v of ui minus 1 vj minus 1 times delta v. And when I take those magnitudes, I can pull out those scalars delta u and delta v. So I can just write this as a sum over I equals 1 to n, sum over j equals 1 to n, of r sub u of ui minus 1 vj minus 1 crossed with r sub v of ui minus 1 vj minus 1 times delta u delta v. And that's equal to the previous sum from before. This should look really familiar from back when we were doing these double integrals. In particular, as I take the limit as m goes to infinity as n goes to infinity. So I'm taking the limit as I use more and more quilt patches. The sums are going to become integral signs, and the delta u is going to become a du, and the delta v is going to become a dv. So the surface area will be the double integral of r sub u crossed with r sub v du dv. And this is my surface area equation, and it's the magnitude of that vector, r sub u crossed with r sub v. And since I took the limit, this is now not an approximation, this is an equality. So this is the equation that we want to remember. The surface area is the integral of that particular expression. So let's do an example. In this example, I want to find the surface area of a sphere of radius a. So let's try to do that. First of all, I want to come up with a parametric equation describing a sphere of radius a, and I can use spherical coordinates to do a good job of that. For example, I could take r of uv. Here, to get a sphere of radius a, I'm just going to take rho to be a. So in terms of spherical coordinates, it's going to be, I'm just going to take my v to be play the role of phi, and u to play the role of theta. So the x coordinate is going to be a sine v cosine u. The y coordinate is going to be a sine v sine u, and the z coordinate is going to be a cosine v, and I accidentally wrote a b there. Let me correct that in a second. And the range of u is going to go between 0 and 2 pi, because I'm going full circle there. And the range of my v's is going to go between 0 and pi, just like phi does in spherical coordinates. So this is a parameterization of the sphere. Let me get rid of that b there. It's supposed to be an a again. There we go. So my sphere here looks like this, and it intersects with the x, y, and z axes at a each time. And so the surface area of the sphere is going to be the double integral, and I'm integrating in the uv plane from 0 to pi in v, and from 0 to 2 pi in u, of r sub u crossed with r sub v magnitude du dv. I just need to calculate this expression. But to start out, of course, what I'm going to want to do is calculate that cross product and try to get its magnitude. That's going to be the tricky part there. So starting out, let's get r sub u. When I do this, I'm just getting the partial derivatives of each component with respect to u. So the first one is going to be minus a sine v sine u. Second component is going to be a sine v cosine u. And the third component is going to be 0. Similarly, let's get r sub v. And this gives me a cosine v cosine u. A cosine v sine u, and minus a sine v. So I want to take their cross product here, and I can cheat a little bit. Write down ru cross rv, that's what I'm trying to calculate. To get this, I can cheat a little bit just by making a fake matrix here, I hat, j hat, k hat. Let's make this big matrix here, I'm just thinking about in red, and take the cross product there. So the first entry is going to be I hat times the determinant of that latter 2 by 2. So it's minus a squared sine squared v cosine u. The middle entry is going to be j hat, so it's going to be minus a squared sine squared v sine u. And then the third entry looks really complicated, but it can be simplified quite a bit. In particular, I'm going to have a sine squared u plus a cosine squared u, so that's going to become 1 when I simplify this thing all out. So the third entry becomes minus a squared sine v cosine v, getting rid of that sine squared u plus cosine squared u term. So that's Ru cross Rv, and the magnitude of Ru cross Rv, let me put some vector symbols there. There we go. This is going to be, again, I'm going to have sine squared u plus cosine squared u. That'll be equal to 1. I can actually factor out a common factor of a squared sine v, because that's multiplying each term, and just take the magnitude of the resulting vector, which is going to be sine v cosine u, sine v sine u, cosine v. I can ignore that minus sign because I'm taking absolute value. And the magnitude of that latter vector is going to be the square root of sine squared v cosine squared u plus sine squared v sine squared u plus cosine squared v. And again, sine squared plus cosine squared is 1, so I'm going to replace sine squared v cosine squared u plus sine squared v sine squared u with just sine squared v. So this expression is a squared sine v times the square root of sine squared v plus cosine squared v. And that's 1 as well. So all I get in the end is a squared sine v. So this is what I'm integrating. I'm integrating a squared sine v to get the surface area. So the surface area is the integral from 0 to pi, integral from 0 to 2 pi of a squared sine v du dv. When I do that integral, when I integrate sine, I'm going to have minus cosine, which I'm going to evaluate from 0 to pi, which is just going to give me 1. So this is going to give me, all told, well, let's just integrate the u first. So it'll be integral 0 to pi of 2 pi a squared sine v. When I integrate that, I'm going to end up with 4 pi a squared. There we go. And this matches exactly with the equation for the surface area of a sphere, because the surface area of a sphere of radius r is 4 pi r squared, and we got 4 pi a squared, and this was the sphere of radius a, so everybody's very happy.